All right, so here we go. This is section 6.3. So our essential question for this section is, what are some of the characteristics of the graph of an exponential function? So now we're going to look at our learning targets. Our first learning target is to identify and evaluate exponential functions. Then we're going to graph exponential functions, and then finally we're going to solve real-life problems involving those exponential functions. So here you will see example 1, and this is where we're going to be identifying functions. So we want to figure out if the table represents a linear or an exponential function. We have to figure out why it is. So the first thing we have to do is figure out how x is increasing. So I see from here to here I go up 1, and then again I continue to go up 1, and I go up 1. Right? This is the first way we decided if things were even functions. So now I want to look at the y's. So I see that every time I go up 1 in my x, I go up 2 here, and I go up 2 here, and I go up 2 here. So this is something that we've seen a lot before. So this rate of change is constant. So since this number is the same every single time, this table represents a linear function. So now let's look at b. So again, I see that my x is going up 1, and again up 1, and again up 1. So that is consistent as well. But now let's look at the y's. So I see I went up by 4 in this first time, and then from here to here I go up 8. So now I can see that these are not constant, but I want to see if there's a pattern here. So I see that I go up by 4 and I go up by 8 up by 16. So that's not something that's similar. I can't quite figure that out. So let's use a different color and see, is there something I can multiply every time to get there? Well, I know to get from 4 to 8, I multiply by 2. Well, and then to get from 8 to 16, I multiply by 2. And to get to 32, I again multiply by 2. So here that I'm multiplying by the same number, this is an exponential function. And that's how we can tell, is because here I have to multiply by something to get my next term, whereas in my linear functions, I could just add the same thing. So now I can determine if my function is linear or exponential. So now we're going to be evaluating. This is example number 2 if you're following along in your book. So I need to evaluate each function for the given value of x. And remember, when I see evaluate, that means I'm just plugging it in and trying it out. So let's look at a. So I've got y equals a negative 2 times 5 to the x, for x equals 3. So the first thing I do is I substitute. So y equals negative 2 times 5, and my x is now 3, right? Because I was told that that's what we're looking at here, up at x equals 3. So now I'm given this math problem, and I know I always have to do exponents first. So I know I really have something that looks like this, times 5 times 5 times 5, right? This exponent just tells me how many numbers go here. So I know that 5 times 5 is 25, times another 5 is 125. So that goes in my parentheses, and I always want to use my parentheses. So now that I'm here, now I can go ahead and multiply by that negative 2. So I end up with a negative 250. So here is where I've fully evaluated by replacing that x with the 3. So now let's look at this function, part b. So I've got y equals 3 times 0.5 to the x. And here I'm told that my x is a negative 2. Okay? So the first step I really need to do is deal with my negative exponent, right? Because I don't like having negative exponents. So that's going to be the 3 stays where it was, the 0.5, and I always want to keep things in parentheses, squared. So now I have 3 divided by 0.5 times 0.5 gives me 0.25. Or 3, and I know that 0.25 is the same thing as 1/4. So now I have a fraction in the denominator, and I don't like that, so I'm going to multiply by the reciprocal to get that out of the denominator. But what I do to the bottom, I have to do the top, so I multiply the top by 4/1 as well. So this equals 12. There's some more examples where we have to work with this. And always remember that we have to follow our order first. We want to get rid of any negative exponents or 0 exponents before we even start. So now here's some monitoring progress. Here's a good chance to try what we've already just done and to try and figure out if you can do it on your own. So here's our big core concept, right? Our second learning target was graphing exponential functions. So here's what we're looking at. So here's the function, the base, the parent function that we're working with, right? So I've got an a value, and in our last example, in this example, my a value, right, was this 3 or this -2, and those have a certain special meaning, and we'll talk about them in just a little bit. So you'll see here that a is kind of my starting value, right? It's when x is 0, and remember, because anything to the 0 power gives me 1, a is where I start, and then I continue to climb. So you'll see that my graph looks sort of like this. When a is positive, so greater than 0, and when b is greater than 0, we're following this blue graph. So when a is less than 0, but b is still greater than 1, we're following this red graph. Okay, so now here we're looking at decay. We're going to call this one our decay. So when I start big and I go smaller. And you'll see that happens when b is a fraction, right? And so that's how I always remember it, is fractions are small, and so I'm getting smaller. B can be anything greater than 1 here, so that's a pretty big number, so I'm going to be getting bigger. That's just my silly way of remembering which direction my graph will be going. So here is example number 3. So we're going to be graphing f of x equals 4 times 2 to the x, and then comparing that graph to the parent function. And we're always going to be dealing with our domain and range. And remember, domain is x values, and range is my y values. So the first thing I want to do is I want to make myself a little table, right, where I have my different f(x) values and my different f of x values. Right? And this is where we just come up with some x values that we want to test. So let's go ahead and test -2, -1, 0, 1, and 2. So all I do here is I take my x value that I have here and I plug it into my original equation. So I've got 4 times 2 to the -1. Well, I know that a -1 flips this down, so I'm going to have 4 over 2 to the first, and I know that 2 to the first is 2, so 4 over 2 is 2. So let's look at 0. If I have 4 times 2 to the 0, 4 times this would give me 4. So I'm just going to fill in the rest of this table real quickly so we can keep going. But that's how we do this. We just plug in our values that we get for x and come up with our points. So from here, now I really just go ahead and I graph those points. All right, so I just pulled over a coordinate plane so we can plot these points. And I see that it's going to get pretty big pretty quickly. So I know that when x is -2, my f of x is 1. When my f of x is -1, I'm at 2. When I'm at 0, I'm at 4. And then 1, 8. And then 2, 16. So I can continue and connect my dots and draw my curve. So I see I can compare this to what we just saw in that core concept and kind of explain what we're looking at. So here I want to look at the domain and range. I know that the domain is all x values, right? And I know that this graph continues on and on and on in both directions. So my domain is going to be all real numbers. And this is just our fancy way of writing all real numbers. Okay, so then I'm looking for the range, and I see that this just keeps getting smaller and smaller and smaller, and it's never really going to meet the x-axis. So my range is going to be y, right, because range always deals with y, is greater than 0. It's never going to touch 0, but it's going to become infinitely close to this. So here's an example of our exponential growth and our domain and range. So here's example number 4. So here I can see I have a fraction, remember? So our graph is going to look more like this instead of what we saw before. So then again, I have to find the domain and range once it's graphed. So again, I make my table of values. And here, right, again, I can use just my -2, -1, 0, 1, and 2. And I just plug those in for my x's, and I end up with -4, -2, -1, -1/2, and then -1/4. So now that I've plugged these in, I can go ahead and graph my points. I'll put it right there. So when x is -2, my f of x is negative 4, when my x is negative 1, we're looking at negative 2 right here, 0, negative 1, 1, 1/2, and now we're just getting really small, right? So I can see that I continue to go like this. And don't forget that, remember, it's down underneath the y-axis because I have a negative a value. So if I look back at that core concept, that means I have my negative and it's going to be on this side of my x-axis. Okay, so now let's look at the domain and range of f. So I see that my domain, again, is all real numbers. And my range here is always y, but I see that y is down below the x-axis, so it's going to be y is less than 0. So now we're going to compare this graph to our parent function as well. So our parent function is just going to be, this is just a reflection over the x-axis. Okay. So the two parent functions that I really look at, this is kind of a big important thing that's not mentioned really well. So here's my parent functions. We look at 2 to the x, right? So this is where my b value is greater than 1. And the other parent function that I look at is 1/2 to the x. So you see that my 1/2 is my b that's between 0 and 1. It's a fraction. You see here I have an a value of 1 because that a changes things, remember. So it's my b, my base, that stays kind of the same here. So these are just my two parent functions. So now here's a couple monitoring progress again. So go ahead and try these ones and see how you're doing. So this right here is going to be example number 5 if you're following along in your book. So here I'm supposed to graph y equals 4 times 2 to the x minus 3 plus 2. Describe the domain and range. So this we looked at in example 3. We looked at something very similar. We looked at the graph of 4 times 2 to the x, right? And we talked about domain and range for that one. So what do I see that's happened from that? Well, I see that my exponent here has this x minus 3. So what does that do? That minus 3 translates my graph 3 units to the right. Right? And remember that if it's with the x, it moves it left and right. And then I see I have this 2. The 2 will translate 2 units up. Right? And because it's outside, it's not with my x, that tells me it goes up and down. So I know that I'm going to have a graph that looks a lot like this, right? Because here was our 4 times 2 to the x. Here was my parent function for this one. And what I've done to it is just made those translations. So I know that I've just translated my graph 3 to the right and translated 2 up. So what I notice about this is my domain does not change. So my domain is still going to be all real numbers. The range is the thing that changes here. So it's still a positive, right? It's still going up, but I've shifted my whole graph up by 2. So now my y is going to be greater than 2. So you'll notice here too is that when my b value and my a value are both, my a is positive and my b is greater than 1, this value right outside here, if we have one, will become my range value. Okay, so here we're looking at example 6. An exponential function g models a relationship in which the dependent variable is multiplied by 1.5 for every 1 unit the independent variable x increases. Graph g when g of 0 equals 4, and then compare g and the function f from example 3 over the interval x equals 0 to x equals 2. So the first thing I want to do is I want to find some points. So if I know that 0, 4 is 1 point, because I'm told that. So I'm told this 1 point. I want to find a couple points to the left and then a couple of points to the right. So I know that for every point to the right, I'm going to multiply by 1.5. So I'm going to multiply by 1.5. And I'm told that from up here. And I know that when I'm going to any points on the left, I'm going to divide by that 1.5. Just because this is where I'm at now, I know that I can go up this way and I go down a little bit this way. So I'm dividing to the left and multiplying to the right. So then I end up with my table of values, right? And here we're looking at G. So my x is -1, 0, 1, 2, and 3. I like to do more positives just because it makes my life a little bit easier. All right, we knew that 0, 4 was one of our points. So if I divide this 4 by 1.5, I end up with 2.7. When I multiply 4 by 1.5, I get 6. Now I'm going to multiply 6 times 1.5, and I get 9. And then I might as well do this point number 3. So I multiply 9 by 1.5, and I end up with 13.5. So now that I have this table of values, I can go ahead and plot my points and draw my graph. So here's some more monitoring progress, so check these out. Now here we go, here's our real life problem. This is example number 7. So the graph represents a bacterial population, y, so my population is y, after x number of days. Write an exponential function that represents the population. And then find the population after 12 hours and after 5 days. So here we have some points. So I see that my population is increasing pretty drastically. So first I kind of want to figure out what I'm really looking at. So I want to use this graph and make a table of values, right? So here's my x and here's my y. So I know I have an x at 0, 1, 2, 3, and 4. So that's going to be the start of my table. So when x was 0, y was 3, and then we had 12, and 48, and 192, and 768. So now I have to figure out what I multiply by each time to get my next term, and I like to start at the smaller ones because I can generally figure those out. So I see to get from here to here, I multiply by 4, and also I know that 12 times 4 is 48. Then I know I can continue this pattern to find where I'm going. So I need to figure out how I can write the rest of my function. Okay. So one thing I know is that my a value, right, and here's the parent function, here's kind of where I'm at. This a value is where I start, is always going to be my y-intercept. So a is my y-intercept. So when x is 0, my a is 3. So here my a will be 3. This b value is how much it changes. So in this example, right, I found that I multiply by 4. So here is my equation and my exponent there. So where I start, how much I change, and then my exponent. So here's my population. Here's part A to this problem. So then in part B, I'm trying to find the population after 12 hours and 5 days. So again, I just take what I have and I substitute. And remember that we were given x, and we're told up here that x is in days. So I know if I'm looking for 12 hours, my exponent is going to be 1/2. And when I'm looking for 5 days, my exponent will be a 5. So now I can just use my calculator and simplify and solve that. So you should end up with my population after 12 hours was 6, and then my population after 5 days was 3,072. Once we go ahead and do this exponent and then multiply. So all we have left is this last little monitoring progress, which is very similar to what we just did, to what we had. So really try this one and see where it gets you. So now let's look back at our learning targets and see how we did. Okay, so identify and evaluate exponential functions. That's what we did on this first page, was trying to figure out that when I add, it's linear, and when I multiply, it's exponential. Then I'm supposed to graph exponential functions, which I did using these different keys, and then solve those real-life problems involving exponential functions. And a lot of our real-life problems will be dealing with bacteria or populations. So those are our big learning targets, which I think that we did pretty darn well. So let's look at this. So I want you to think in your notebook and say, finish one of these sentences. I made progress with something today. Did you learn something about exponents or exponential functions? Or tomorrow I need to figure something out. or right now I know this. Take a minute to just figure this out and just reflect on what you did today before you start looking through the homework problems.